Hi, and welcome to our introduction to stochastic gradient boosting for regression. Now, before we actually go into the material, I highly recommend that you first watch the video Introduction to Cart Decision Trees for Regression. And the reason is because, as we'll see in this video, cart turns out to be the foundation of stochastic gradient boosting. Now, a dataset that you'll see referenced in these slides is the concrete strength dataset. Here the goal is to predict concrete strength, which is a quantitative target, using these predictors. Now, this dataset was obtained through the UCI Machine Learning Repository, and here's the academic reference for this paper, and the person who donated it is here. So here the goal is to predict concrete strength, which is just this column here, using the rest of these variables as predictors. Okay, so the main idea of stochastic gradient boosting is to iteratively fit cart trees to what we call generalized residuals. Now, the creator of this technique is Jerome Friedman, who's pictured here. And so Dr. Friedman also co-created cart decision trees, Mars regression splines, and even co-created rule learner rule ensembles. And in fact, he's actually created a wide variety of other machine learning algorithms. You don't really have enough space here to kind of list them all. So he's quite prolific in this field. Now, the SPM modeling engine that implements the stochastic gradient boosting algorithm is called TreeNet. And so you'll see some snapshots from TreeNet in this presentation. And in the next presentation, I'll actually provide you with a hands-on demonstration of stochastic gradient boosting using TreeNet. Now, just so you know, the code used for TreeNet was actually originally written by Dr. Friedman himself. Okay, so stochastic gradient boosting is the formal name for this technique, but here we're just going to call it gradient boosting or gradient boosted trees. Now, sometimes people just call it boosting, but there are actually different types of boosting algorithms, so really just to kind of distinguish gradient boosting from the other types of boosting algorithms, we'll just stick with gradient boosting or gradient boosted trees. Now, stochastic gradient boosting can be used for a variety of things, including regression, classification, survival analysis, and there are actually even more applications. Now, the reason that gradient boosting is used is because it is one of the most powerful machine learning algorithms in existence. And it also tends to be really very fast, even for larger data sets. And finally, because, as we'll see, since CART serves as the foundation of this technique, you can actually build models with dirty data. I'm going to now introduce the gradient boosting algorithm using the least squares loss function. Least squares is just here, so this is just where we evaluate our error based on taking the y value, subtracting its prediction, which is just this y hat, and then squaring it, and then taking the sum. Now, here in this case, the main idea is first you supply an initial value, which is just the overall average of the target variable. And then what you do is you sample some records randomly. And for the record sample, you just fit a cart tree to the residuals from the previous step. And then you use this tree that you've built here in step 3 to update the model, but you just shrink the update by a small number. And then you just repeat steps 2 through 4 m times. And you as the user are going to supply the m. Now, this is just kind of the sketch. And so what we're going to do now is we're actually going to go into the algorithm in detail. Okay, so remember we have a least squares loss function, which is just given here. And as I mentioned, for the least squares loss function, the initial prediction, which we just denote with f0 here, is just the average of the target variable for the records in the learned sample. So f0 here is just going to be y bar, which is just the sample mean for the target variable. Now what you're going to do is you're going to draw a random sample, and we'll call it S, from the records in the learned data. So you'll have some sample. And then what you're going to do is you're going to compute the generalized residual. Now for the first iteration here, the generalized residual is just y minus the y bar for the records that you sampled here in S. And so you're going to have this y tilde here as your target. And so using this y tilde as the target variable, you're going to fit a small unpruned cart tree with j terminal nodes using the records in S. And so you'll have your sample here, and you'll have this y tilde as your target, and so then you're just going to fit a tree. Okay, and then you're going to use this tree to update your model. So for the least squares lost, the updates here are just going to be the target variable average for each terminal node. And we can denote these updates for the first iteration by cart1. And so for the fourth step, what you're going to do is you're going to shrink the updates from step 3 by multiplying by what we call the learning rate. Now the learning rate, so alpha here is really just a small number. It's like 0.01 or maybe 0.1, and we'll spend some more time on that later, actually understanding the learning rate. But what you're going to do is you're going to shrink the updates by alpha, and then you're going to add them to the current model, which in this case is just f0, and you'll then obtain an updated model, which we'll call f1. So your updated model is here, f1, and this is going to be equal to f0 plus alpha, which remember is the learning rate, times the updates, which are just we represent by cart1. And so now we have the formula here for f0, so we can actually just plug in. So really it's just y bar plus our shrunken updates. So this is iteration 1. Now for iteration 2, our current model now is f1. And what we do is we just draw a random sample S from the records in the learn data. So we'll have another sample. It'll be different from the one in the previous iteration. And now we compute the generalized residual. So now it's going to be y minus f1. And so you'll have still that y tilde again. It'll be different from the previous iteration. Now the question here is, well, how exactly do you compute this? How do you exactly compute this generalized residual? Because y minus f1 is equal to this. So you have your y value here, which is just a number, then you have y bar, but then you have this update. And so now I'm going to explain what this update actually means. So the current model after the first iteration, if you'll remember, is just y bar plus the alpha, which is our learn rate, just that small number again, times cart1. And so our generalized residual that we need to compute here is just y minus that f1, which is just equal to this. Now remember, cart1 is just the tree fit to the generalized residuals during the first iteration, and the generalized residuals during the first iteration was just yi minus the y bar. And remember, alpha is just that small number. So let's suppose that cart1 is a tree that looks like this. And so for now, what we'll do is we'll just give y bar a number, maybe 40, and then we'll let alpha also have a number, so it's 0.01. So, and then we'll have some randomly selected record. And so maybe the record looks like this. Okay, so the value for cart1 then is just the terminal node average after running the record down the tree. So we have our record here, and we're going to run it down the tree. So here we have x2 is less than or equal to 17.5. Well, what's x2 here? Well, it's 12.5, so we'll actually go to the left here. And then, is x1 less than or equal to 355.8? Well, here x1 is 400, which is greater than this number. So we're actually going to need to go to the right where x1 is greater than 355.8. So our record ends up here. And our predicted value, if you remember from our previous video on cart decision trees for regression, is just the node average, which is here. And so the value for cart1 is just this number. And so what we can do is we can now compute our generalized residual. We have values for everything. So y is just 39, which is given here. Y bar we supplied before, which is 40. Alpha we also supplied before, and that's 0.01. And then cart1 we just computed, which is here, so we can just plug in, and then we get this value. And so this is our generalized residual for this record. Now what you do is you just repeat this process for all of the records selected in step 1, which is just here. So step 1 is just when we draw that random sample. So you're going to draw that random sample, and you're going to perform this process that I just explained for all of the records in that sample. So that is how you compute a generalized residual, using the least squares loss function. Okay, so now we know how to compute our generalized residual. So what we'll do is we'll just set our y tilde, which is just our generalized residual, as our target, and then we'll fit a small cart tree with j terminal nodes to this target, using the records that we had in step 1 here. So we'll have our sample again, and we'll fit a cart tree. And what we'll do is we're going to use this tree to update our model now. And remember, the updates are just going to be those target variable averages like we saw in the previous slide. And we'll just call these updates cart2. And what we'll do is we'll shrink the updates by multiplying by the learning rate, which is that small number. And we just add them to our current model, which is now F1. And that'll give us our updated model F2. So here's our updated model. And remember, we actually do have the formula here for F1, so we can actually just plug in. And so this is our now updated model after iteration 2. Okay, so for iteration 3, it's going to be the same thing. So now we have our current model of F2. And we'll draw our random sample. We're going to compute our generalized residual now for F2. And then we're going to set the generalized residual as our target, and then we're going to fit a cart tree to this variable. And then we're going to use the tree to update the model. And remember, the updates are just going to be those target variable averages again, and then maybe we'll call these updates cart3. And we're going to multiply those predictions again by the learning rate, and we'll add them to our current model. And so here's our update model now is F3. And so we have the formula, remember, for F2. So just plug this in here, and then you're going to get this for your updated model. And so then you just continue this process over and over and over. And I'll skip here to the last iteration. So just as a note, there are a total of m iterations, and in practice, you as the user, you're going to actually specify the m. And we're going to talk about how to choose m, but we'll get to that later. So our current model here is fm minus 1. And so here we have our y bar, and we have m minus 1 cart trees. And so what we'll do now is we're going to draw our random sample again. We're going to compute our generalized residual now for y minus f of m minus 1. And then what we'll do is we'll use this y tilde as our target, and we'll fit a cart tree to this using the records that were selected in the sample. And then we'll have another update, which is we'll call cart m for iteration m. And we'll do the same thing. We'll shrink by alpha, and we'll add it to the previous model, or sorry, the current model, and we'll get our updated model here. Now again, of course, we have the formula here for fm minus 1, which is just here. So we'll plug that in, and this actually is our final model. And so this is the stochastic gradient boosting algorithm for the least squares loss function. Okay, so how do you predict new records? Well, let's just suppose that we have our final model here, which is just the sum of cart trees. And so we have m iterations and m cart trees. And so that's something just kind of important to note. And now the reason that's important is because depending on the software that you use, you're either going to see the number of trees, or maybe you'll even see number of iterations. And so for TreeNet software, we actually use number of trees. Now, to predict a new record, what you do is you just run the record down each tree, each time that computes a prediction. So we'll have our initial value, that's just going to be the y bar, so you're not running that down a tree. But take your record and run it down cart 1, you're going to get a prediction. And then down cart 2, you'll get another, and so on. And then what you do is you multiply each value, except for the initial value here, which is the 42, which is our y bar, by the learning rate. So go ahead and multiply all these values by the learn rate. And then, to get your final prediction, just add the values from step 2. And just for the sake of example, we'll go ahead and let alpha be 0.01. And so this is your final prediction. So this is how predictions are obtained in stochastic gradient boosting. So when you're building gradient boosted trees, just keep this picture in the back of your mind. Your gradient boosted tree is just an initial value plus the updates from these cart trees that are fit to the residuals, and they're shrunken by the alpha. And remember that there are m of them, and you're going to choose the m. Okay, now because the foundation of gradient boosting is cart, gradient boosted trees automatically handle the following. So variable selection, interaction modeling, and all of the other advantages we discussed in the cart video previously. So the introduction to cart decision trees for regression, all of this is covered. Now, one thing that I will note is that missing values are handled slightly differently in gradient boosting than they are in cart. We don't really have time to get into it in this video, but in cart they're handled via surrogate splits. In gradient boosting there's a different way to handle them that's faster. Now, what does all this mean for you as an analyst? Well, what this means for you is that you can build gradient boosted trees with dirty data. We just saw the gradient boosting algorithm using the least squares loss function, but gradient boosting actually is more general in nature, and you can actually handle a variety of loss functions. So just one thing to kind of keep in mind is that depending on the loss function that you choose, this is going to change the formulas used for the initial value, the generalized residuals, and the model updates. But as you can see, we have like least absolute deviation. This is like the absolute error. We're actually going to show an example of this on the next slide. Also, you can handle survival data. If you have gamma is for if you have positive targets. Negative binomial and Poisson are for count targets. Now, binomial is for binary classification. Multinomial is for multiple classification. And you even have some differential lift modeling options as well. So gradient boosting is actually a very flexible algorithm, and it can handle a variety of different types of problems, which makes it a very attractive technique. Now, just to kind of give you an example of a different loss function, here we have the least absolute deviation loss function, or LAD. LAD is just the absolute error here. And so the process for constructing the model itself is exactly the same, except the only thing that changes is that the generalized residuals become the sign of the typical residual. The model updates are just the target variable medians in the terminal nodes as opposed to the target variable averages. And now the updated model is still the same, and the overall, the initial prediction is just the overall median. And so that's the difference. But other than that, the process is exactly the same. Okay, so now what we're going to discuss is how to tune gradient boosted tree models. And so there are actually a number of parameters to consider in gradient boosting, and they include the number of trees, the learning rate, the subsampling fraction, and the tree depth. Now, the optimal parameter setting is actually it's always going to be dependent upon a particular data set. So the only way to know the best values is just to experiment and try different values. And we'll talk about some efficient ways to do that. Okay, so the first parameter to discuss is the number of trees, which is also, remember, the number of iterations. And so this is your M in the algorithm we discussed previously. So each iteration in a boosted tree model corresponds to a single cart tree fit to the generalized residuals from the previous iteration. And remember, just the number of trees is equal to the number of iterations. Now, the number of trees should be set high enough so that the model error converges. And one thing to kind of keep in mind, though, is that sometimes you're going to see that after a certain number of trees, the test error curve will start to actually increase. So it'll decrease, 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 and then it'll start to go up. And so at that point, what you'll do is the number of trees that you'll choose will just correspond to the minimum of the error curve. Okay, and the optimal number of trees, that's going to be dependent upon the other model parameters. So it'll depend, but the number of trees, just make sure it's set high enough so that the model error no longer meaningfully declines, or until maybe it even starts to increase, depending on your data set. So to give you an example, first of all, this is how you set the number of trees inside of SPM. Now, as an example of the number of trees, we can kind of see that here there's not really a material improvement in the error after around 300 trees. So the default here is 200, that's our default in our software, and 300 is actually around here. So as you can see, the error curve is largely the same after around 300. So even if you increase the number of trees by a factor of 3, I mean, you're around 900, and it's really about the same. So just make sure that the error is no longer materially declining, and if that's true, then you can stop. So the next parameter we'll discuss is the learning rate. Now remember, the learning rate, which we just denoted by alpha, this is just the amount of shrinkage applied to each model update in the jth iteration. So here, for any iteration, at iteration j here, we just shrink the updates by this factor of alpha. Now, the learning rate is always between 0 and 1, and choosing the optimal learning rate, the way you do this is you can do this through either cross-validation or you can do this via a testing sample. The general rule of thumb, though, is that you want to keep this learning rate small, and values like 0.001, 0.01, or 0.1 often give pretty good results. But one thing you should just be aware of is that smaller learning rates do require more trees or more iterations. So just to kind of elaborate a little more on the learning rate. So again, we set the learning rates to be smaller, and smaller learning rates do require more trees for the model error to converge. Now, the intuition as to why this is true is the following. So imagine that you want to walk to the middle of a crater, so here. And if you take small strides, now a small stride would correspond to a smaller learning rate, then you're going to need more steps meaning more iterations, to get to the bottom of this crater, meaning to get to the minimum error. Now, if you make a mistake, which in the case of our analogy here, meaning the model maybe makes an error during one of the iterations, then the error really is not as serious because your stride is smaller. And so what this means is that in the next iteration, it's easier for the model to recover. Now, if you take larger strides, meaning you have a larger learning rate, then you will need less steps to get to the bottom of the crater. So you'll need less trees to get to the minimum error. But the issue here with larger learning rates is that if you make a mistake, meaning that the model makes an error during one of the iterations, then the error is going to be more serious because your stride is larger, meaning you've kind of pushed in a certain direction more than you perhaps should have. And so it's not as easy for the model to recover as compared to the situation where the learning rate is smaller. And so we want to keep the learning rate smaller. Now, one thing to kind of note is that, yes, you'll need more iterations with the smaller learning rate, but remember, when we're actually fitting these cart trees are actually very small, and they're actually unpruned. So you can actually fit a large number of cart trees quite quickly, and that's actually one of the advantages of gradient boosting. Okay, so just to give you an idea of gradient boosting and how it actually models one of these curves, let's actually just see how the prediction from a gradient boosted tree evolves. Now, one thing to keep in mind is fundamentally the way gradient boosting works is you make these very small improvements. And the reason they're small improvements is because, again, our learning rate is a small number that shrinks those model updates. So when we shrink those model updates to be small, that's why you have these little teeny tiny improvements. Okay, so we have our initial value, which is just our average. And then we have our first tree here, which is this dotted line. Now, so we can see this dotted line here, just off of the average. And then here's for the 10th tree. So at the 10th tree, you can start to see that this portion of the predictions are starting to kind of rise, whereas this portion, they're actually starting to become lower. Now after the 50th tree, we're here, and we can start to see that our model is really starting to take shape of this curve. And again, the reason we're just kind of inching up is due to that learning rate, because we're shrinking the model updates each time. And so here it is after tree 100, and here it is after tree 150, and you can see that we're just continuing to inch toward our curve here. And notice here that this portion is actually starting to become better approximated as well. So tree 200, we're getting even better. And here's at tree 400. You can see quite a jump here. And so now we're actually really starting to get into this portion of the data as well. And here it is at tree 600. So here's the final tree here at 600. As you can see, we made these little teeny tiny improvements, but the final model is actually really very good, considering that we started with just the overall average. Okay, so if you want to experiment with different learning rates without having to manually refit a model each time, then we recommend that you use Automate Learn Rate. So Automate Learn Rate, what it does is it automatically builds separate TreeNet models with a different learning rate each time. And all the other model settings are left identical, so the only thing you're actually changing is the learn rate. And we'll go over this in the next applied video. Okay, so the next tuning parameter is the subsampling fraction. And so remember that in the first iteration, in the first step of the gradient boosting algorithm, we draw a random sample from the records in the learned data. And so the question is well, why even take a random sample in the first place? Well, taking a random sample at each iteration, what this does is it decreases the correlation between the trees at different iterations, and this tends to reduce the overall prediction variance of the combined model. Now, you may ask, well, how large should the random sample be? Well, the answer is that it always depends on the data set, just like anything else in machine learning. Now, the default value is 50%, and one thing to kind of keep in mind is that when you have really large data sets, just kind of keep the random subsample in mind, because smaller percentages lead to faster model compute times. And the reason is because there is a smaller number of split points to evaluate for each cart tree. And so if you'll remember from the previous video, which is the introduction for cart decision trees for regression, we discussed that cart computes all possible split points. And so when you have a smaller sample, then you have a smaller number of split points to evaluate, which speeds up the compute time. And by decreasing this subsampling fraction, depending on the data, it may or may not affect the accuracy of the model. So it's always something to experiment with. And so here's where you set the subsampling fraction. And if you want to experiment with different values for the subsampling fraction, we have Automate TN subsample. So this is just another automated procedure where what you do is you fit multiple gradient boosted trees, but each time you just change the value of the subsampling parameter. So maybe you start with 10%, maybe 20%, 25, 30, 40, and so on. And you can of course specify whatever values you'd like. Finally, we're going to discuss tree depth. So the tree depth, what we mean by this is just the maximum number of terminal nodes per tree. So in gradient boosting, the user, you yourself, you're actually going to set the maximum number of terminal nodes for each cart tree. And now a cart tree with j terminal nodes can capture up to a j-1 way interaction, although it is not guaranteed that a j-1 way interaction will be modeled. Now, as an example, if the maximum number of terminal nodes is set to maybe 7, then a boosted tree can capture up to a 6-way interaction, but it's not really guaranteed. And we'll have an example as to why that is. But just in general, as the number of terminal nodes increases, the complexity of the interactions able to be modeled increases. So as an example, let's look at this cart tree using that concrete data set that I mentioned at the beginning of this video. Now, the picture that you see here is actually automatically produced with cart software, and you'll recognize this from the applied examples in the previous video. So this shows a cart tree with 5 terminal nodes. So we have 1, 2, 3, 4, and 5 terminal nodes. So each one of these red boxes. Now, the tree on the left here models the following. So the first is a 2-way interaction between water and fly ash, which is actually what you can see here. So we have this portion here. This is actually a 2-way interaction between these two variables. Now we also have a 2-way interaction between water and fine aggregate, which is here. So just these two by themselves. Now furthermore, we also have a 3-way interaction between water, fine aggregate, and coarse aggregate. So this portion of the tree. And so what we can learn from this is that Here we have a 5-terminal node tree that captured a 3-way interaction as opposed to a 4-way interaction, which is the largest interaction order that it can actually capture. So this is what I mean when I say that just because you have maybe 5 terminal nodes doesn't necessarily mean that you're going to actually capture a 4-way interaction. It's not guaranteed. Now, a more detailed explanation of this topic, how interactions are handled in cart trees, is actually provided in the following videos here, and the links are actually going to be below. Make sure though that when you're doing this that you watch these 2 videos in order. So watch the how to write a decision tree as an equation first, and then how cart handles interactions second. Okay, so now we're going to move on to the final topic of this presentation, which is interpreting a gradient boosted tree. So since a gradient boosted tree is fundamentally a sequence of hundreds or thousands of cart trees, there's not a tree diagram like there is with one cart model. Now, of course, there are some options for interpreting gradient boosted trees, and today we're just going to discuss variable importance measures and partial dependency plots. Now, the variable interaction statistics and rules we'll discuss in a future video. So the way that variable importance measures are computed in gradient boosting is that each time a variable is used to split the data, an improvement score is recorded. Now, the variable importance measure itself is computed by just summing the improvement scores every time a variable is used in any of the trees. And so you'll see variable importance measures like this. And if you check this relative importance box, then they'll be scaled here. Now what this actually does is you divide each of the raw importance scores, which are on the left here, by the largest score, and then you just multiply by 100. So in the case of age day, it has a score of 1, and so we divide it by 1 since 1 is the largest score. We multiply by 100, and then you get 100, which is what you see here. Now for the super plasticizer, what you do is you take its value, 0.3859, divide by 1. Remember, 1 is just the largest value. And then multiply by 100, and then you get 38.59. Now here it says 0.39. That's just kind of a rounding the way it's presented. So that's why it's 38.59 as opposed to 39.0. So that's just kind of a rounding thing based on the display. Okay, so the way you interpret this is that age day is around 2.5 times as important as super plasticizer. Because if you take, so this is around 0.4, so 0.4 times 2.5 gives you 100. So you can say that age day is around 2.5 times as important as super plasticizer. And so that's why you use the relative importance measure. Okay. So our next topic is partial dependency plots. So partial dependency plots show how a variable, or set of variables as we'll see, affect the average response of the model after accounting for the other variables in the model. Now partial dependency plots can be created for both categorical and numerical variables. And so the way they're constructed is the following. So let's for now just assume that we've built a gradient boosted tree, and we'll call it Tn of x, Tn for TreeNet. And we're going to sample a single record R. And so here's our single record. I couldn't fit all of the other variables on this one page, so that's why we have these dots here. And so what we'll do is we're going to hold every value in the record constant except for the value for the variable under consideration. So for instance, if you wanted to construct a partial dependency plot for the variable age day, then you're going to leave all of these values constant, and you're just going to change this value. So what we'll do is we'll just plug this record as it is right now, the original record, into the TreeNet model. And that's going to give you one predicted value, which is here. And then what you can do is you plug this record in again, except for this time you change the value for the variable under consideration. So maybe you change this to maybe 10, plug this in, and you'll get this value. And then just do this multiple times, which generates multiple points. So maybe change this to 60, you get this. Change this to 80, and you get this. Maybe 175, and you get here. And then you keep doing that over and over. And then you just connect all these points, and that forms one curve. And now what you do is you repeat steps 1 through 4 multiple times, which results in multiple curves. So take a new record and then plug it in, and then keep changing the value for the age day variable, and that's going to give you another curve. And then just keep doing this. Now what you do is you just take the average of all the curves generated to yield the final partial dependency plot, which is here. Okay, so how do you actually interpret this plot? Well, the first thing I like to do is I like to just look at the directional aspects of it. So what you can say is that as the age of concrete increases, so age is the x-axis here, so as this number gets larger, you can say that the average concrete strength increases, and it actually becomes constant here. And so when you're interpreting this plot, just kind of focus on the direction. So see where it increases, and also just see where it's constant or decreasing depending on the plot. Now to be more specific about the interpretation, you can say that if age day increases from, say, maybe 1 to 100, then the average concrete strength increases by 27 after accounting for the other variables in the model. And so we get this 27 because at an age of 1 day, you're at around -12, and then at around 100 days, you're at 15. Now, note here that you can only use this plot to examine the change in y as opposed to the actual value of y. So this is a marginal plot. So you're only looking at the change in y for increasing the variable age day. Don't take the values for y literally by themselves. So don't say, oh, at age 100, the concrete strength is 15. No, that's incorrect, because the actual value for y is going to depend on the values for the other variables. So you only use this as just the marginal plot, looking at the increases or decreases, or even where it's constant, for a variable. Okay, so we just showed you the partial dependency plot for one variable. You can generate them actually for 2 variables as well. And so here the procedure is exactly the same, except for now we're doing this for 2 variables, and we're going to vary both of the variables over their entire domain. So, and that will give you a surface. And then you'll repeat the process and you'll yield multiple surfaces. So an example of a 3D partial dependency plot is the following. So here we have one of our predictor variables, age day, and we have another predictor variable, cement amount. And we also have this output. So output here is the z-axis, and so the z-axis is just the average response. And so keep that in mind. This is just the average response. And so what this plot is telling you is that high values of cement amount, especially when you're over 400, so in this region here, result in stronger concrete for almost any value of age day, but especially when age day is over 25. So if you go to, so here we're over 400 for the cement amount, and we need to find age day where it's over 25, so it's probably around here. So if you come up here, then you find yourself in this yellow and this dark yellow portion of the surface here. And so as you move along, especially when you increase the cement amount, then your concrete strength will be higher. And so just kind of keep this color coding in mind here. So when you're in the blue, you're at a lower average concrete strength, and when you're in the red, you're at a higher average concrete strength. Now, if you don't really like that view, you can view this as a heat map where it's a lot easier to see. And so it's kind of hard to pick out the 25 in that previous plot, and here it's a lot easier. You can just go directly over here, and then you can also see that over 400 you especially get higher values. And you can actually even go back a little ways, so it's actually maybe even around 350. So really in this region here is where you have the higher values for the concrete strength. So me personally, I like to actually look at both of those plots, both the 3D and this 2D projection here. Okay, so that actually concludes our introduction to stochastic gradient boosting. And if you have any questions, then please feel free to contact us at support@salford-systems.com, and I'll see you in the next video.